Hello everyone, welcome to our channel, and we have a new circuit here. This is a transistor monostable multivibrator collector coupled. We have the transistor here, LED, lots of resistors, capacitor, two capacitors, LED, and a push button. Every time we push the switch here, LED turns on and slowly turning off. The application of this transistor monostable is just like a dimmer switch. It is believed to be invented early in 1920s using vacuum tube, but here we are using transistor as a monostable multivibrator. So we also have here as previous circuit, also a monostable multivibrator transistor. The only difference is this our new circuit has an LED and the power supply is connected to the header. Here we have no header here, only a push button. Every time you push, also LED turns on, slowly turning off. Also we have this transistor dimmer switch using only one transistor, making the LED to turn on and slowly turning off. And we have this capacitor dimmer switch. All of these circuits are serving as a timer switch. Let us see the circuit diagram of this transistor monostable multivibrator collector couple. The circuit diagram of this is this: two transistor collector coupled, the other one coupled by the capacitor, LED power on indicator, triggering switch to the base of the first transistor, some load resistor, base resistor pull up, and an LED is connected to the transistor 2, where we are going to take the voltage output at the transistor 2. That is the collector output. And in this old circuit, this is the circuit diagram. Very messy, but still the same with our new circuit here. The only difference it has no LED power on. Also in this circuit, we have this, a transistor dimmer switch. So you push the button here, capacitor is charging to the base, and slowly dimming the LED, turning on the LED and slowly dimming it. That is the design. But in here we have this capacitor dimmer switch. Every time you push the switch here, this capacitor dimmer switch, capacitor is charging here and slowly discharging to the LED. All of these four circuits has a capability of controlling the circuit, the LED, the light of the LED. But we are here with the multivibrator transistor collector coupled. Let us examine the circuit diagram of this our new circuit. Pushing the button here, and this is because of the effect of the capacitor connected here. That is the one controlling the light, the LED, in the output side of the circuit. So we have the 5V supply connected. This is the switch, and then the resistor and the LED. This is an LED power on indicator. That is the green one. And since we push the button, circuit on, LED turns on. Closing the switch, LED turns on, current flows into the LED, in series with the resistor. We use this resistor to limit the current flow of LED. Computing the value of the resistor using KVL, Kirchhoff's voltage law, voltage supply minus the voltage drop across the resistor and the LED. Transposition, computation, I use 2 volts. The voltage drop across the LED is 2 volts. That is given in the data sheet of the LED. That is 2 volts. And we get now 3 volts. Calculation. Since we know the voltage drop across the resistor 3 volts, what about the current flow at the resistor? I'm using the Ohm's law. B is equal to IR. Since we are computing the value of RD1 transposition, we get now 3 volts over 0.02 ampere. It means that the current flows at the resistor is 0.02 ampere. That is given in the data sheet of the LED. The voltage rating of the LED and the current rating is given in the data sheet. In order to turn on the LED, we need that value of current, 0.02. So we get now 150 ohms. So we know the value of the resistor here is 150 ohms. And now the LED here is lit up. Also pushing the switch, making this circuit to act or to be in a stable state, the transistor here. So this is the stable state of the monostable multivibrator. The LED is turned off. Let us examine the circuit here. Also current flows here at the switch. We need the switch to trigger the base of the first transistor to activate this. Since the switch is open, current flows up to here. Also current flows up to the RC1. That is the collector resistor. We need that resistor for charging the capacitor here. And it's connected to the capacitor. Did you see that? Upon closing the switch, capacitor here is charging, making the transistor Q1 to operate in cut-off. Almost open. Charging the capacitor to the base and to the emitter. Activating this transistor Q2 to operate in saturation. Also here, there's a pull-up resistor here. Continuous supply of current from BES, supply voltage to the base. And we have this collector resistor. This is also needed because we're going to provide a required collector current to operate this LED. To turn on this LED, I choose the value 0.02 ampere. So this is arbitrary values needed to turn on the LED. I choose this value. IC here is IL here is not given. This load current. I choose this in our design. This is 20 milliampere. And the resistor here, we don't know the value. Since as we have seen here in our circuit, LED is off. It means there's no current at the LED here. And the current flows into the collector emitter junction, making the transistor to operate in saturation mode. Because there is a base current here. We can compute the value of the resistor here using KVL. Voltage supply minus the voltage drop at the RC2 minus the voltage drop at the transistor collector to emitter junction. KVL Transposition, substitution 0.2 volts. Voltage supply minus the voltage drop at the resistor, voltage drop at the collector to emitter. BCE here at saturation 0.2 volts. That is given in the datasheet of the transistor. Usually in silicon type it is 0.2 volts. So we are using BC547B silicon type. We get now the voltage drop. Where is that? .8 volts. BS minus BRC1 CE. Transposition 0.2, 4.8 volts. Voltage drop across the resistor here. To find the value of resistor here, since the required current to pass is 0.02 ampere, needed to light this LED. Using Ohm's law, we get now resistor RC2 is 4.8 divided by required current 0.2, 240 ohms. This is 240 ohms, this is 150 ohms. Since the current flows into the base, we can compute for the voltage drop across RB2 KBL. Voltage supply minus BRB2 and BBE at saturation, which is equal to 0.7 volts. Minus BRB2, BBE sat 0.7, we got 4.3 volts. Voltage drop across RB2 is 4.3 volts. That is the current flows during the stable state of the transistor, taking the output here. We got a voltage drop here. We need the base current to compute the base current, since we know voltage drop here. Base current is computed by using the current gain of the transistor. HFE is equal to IC2, IB2. IC here is 0.02 ampere. The collector current here, or a collector current at saturation, is equal to 0.02 ampere. Since this is shorted. So we get now IC over IB transposition, and we have this HFE. HFE, current gain of the transistor, is given in the data sheet of this BC547B. So by computing that, we got 0.001 ampere IC over HFE. So we know the base current and the voltage drop using KBL and transistor formula. Calculating that using Ohm's law, since we know that 4.3 volts voltage drop across the RB2 and the current is 0.001, we computed that 43 kilo ohms. So the value of this is 4.43 kilo ohms, 240 ohms, 150 ohms. Now, what is the value of the resistor here? The resistor here is also the same as the resistor here. Since we're designing stable state, stable circuit, whatever the resistor here is equal to the resistor here. 240 is equal to 240. You can also calculate that during the saturation mode of the transistor 1 here, KBL. And the collector current here, or the load required current here, is also the same as here. We're designing a monostable stable circuit. Collector current, same here, resistance here, same as resistance here in designing a circuit. So at this state, upon closing the switch, there's no current flows at the switch, and the current flows into the capacitor, charging the capacitor, and then up to the emitter. Complete circuit. Also, continuous circuit is here by pull-up resistor. Also, current flows here, making the LED to turn off because there's no current flows here. As we have said, the resistance here is lesser than the resistance of the LED. So the current flows into the shorted path, or since this is shorted, not in here, so the LED is turned off at this state. There's no current flows here because, as I've said, when the capacitor is charging, it is off. This one is on upon closing the switch. See, LED turns off, charging the capacitor. The moment we apply a triggering pulse here, this is now the current flows. Current flows into the switch, into the base, into the base, also here, into here, making the Q1 transistor Q1 to operate in saturation mode. Also into the LED and into the base of the transistor because of this triggering pulse by the push button in series with the capacitor. 10 microfarad, 16 volts, arbitrary values. I choose this value just to debounce the switch debouncing. Now current flows into the RC1 to the ground. And also, capacitor now is discharging upon applying this triggering pulse. It's now time to discharge the capacitor, dumping to the ground, making this transistor to operate in saturation, almost shorted. And the current here is not flowing to the base. Instead, the current flows into the capacitor. That is the discharging effect of the capacitor. Not here. So this is now open or off. And now, since this is off, current flows here into this two line, making the LED to turn on. See, the LED is now has the current enough to turn on the LED. Also to the base, RB1. We're now going to compute for the value of RB1. RB1 is computed this way, since triggering current here upon application of the voltage supply or supplying a current here. Now this line is now activated from the source to the RC2 to RB1 and to the base. There's a trigger current here. Upon the application or providing a single shot multivibrator, as they have said it, one shot multivibrator, providing a triggering pulse here, activating this line and this one. They can compute the value of this using KBL, voltage supply minus voltage drop here, and in here BE to the ground. Voltage supply minus the voltage at the RC2, BRB1, BBE sat is equal to 0. BR2, BR1, BE to the ground is equal to 0. Now we have, by substitution, we know that the voltage drop according to base and the emitter is 0.7, as I've said. That is the voltage drop at the BE. In the case of silicon, for computation, we're using 0.7 here. We got now 4.3 volts. The sum of the two voltage drop at RC2 and RC1 using KBL. Since in Ohm's law, voltage is IR, using IR here, substitution, IB1 here, the current flows here at that state is I, the base current. We can calculate the base current here using also a transistor formula. This one. almost the same as the previous one. IC over IB, HFE. We got now the base current. The base current here that flows here upon the application of the triggering pulse making to activate this line. The base current here is the same as the base current here. Since the current flows here, so the base current, the current flows here is now 0.001. This is also 0.001, which is IB1 in the case of this formula. Substitution, RC2, 4.3. Since IB1 is 0.1, RC2 is 240. We know the value of RC2 here. Substitution from this formula, we got now this 0.24, 0.20 plus 0.001 times RB1 equals 4.3 minus 4.276. By dividing both sides by 0.001, we got this, and then we have this, and we got 42,760 ohms. That is the value of RB1. Now we all know the value of the resistor needed to conduct the circuit in monostable operation. Pushing the switch here, making the transistor here to operate in saturation, because there's a base current here. Since the two, they are in series. Actually, they are in series because of the triggering pulse applying here, making this to operate in cutoff mode. And then the current flows here, and is slowly decreasing the brightness of the LED as long as the capacitor is discharging here and completely discharged, completely dumping its charge to the ground. Now it will go back to its stable state, this current low. Why the current is not flowing here? Because this is the moment that the capacitor is discharging, making this a negative potential to the base, making this a reverse bias. Current tends to flow here. The action of the discharging speed of the capacitor is from here. RB2 and RC is with the use of these two components. We can compute for the speed of the discharging effect of the capacitor using this RC circuit. See, the discharging is happening here. That's why there's no current flows at the base of the second transistor, because this time, upon applying the pulse, discharging effect of the capacitor takes place. We can compute the speed of the discharging effect of the capacitor using tau, or the time constant, 0.69 RC. That is the standard formula for computing the speed of the discharging effect of the capacitor. I'm using the value of 100 microfarad. I choose the value of 100 microfarad. This is a choose, and we calculated the value of the resistor here. Discharging, no current flows here upon discharging. Microfarad 100 also equal to -6. This one is 43,000, same as 43 kilo ohms. We need a unit of ohms and farad to make a second. We need to be in ohms and farad. 100 times -6 also equal to 0.0001 farad. 2.967 seconds. So it requires 2.96 seconds, almost 3 seconds to fully discharge the capacitor, or to discharge this capacitor. That is this state, quasi-stable state. Now the LED is slowly turning off. If this transistor is operating in saturation mode, LED here will start to turn off. and go back to the charging state of the capacitor here. When the capacitor is again charging, LED turns up. When application of the triggering pulse here, capacitor is discharging. So this is the discharge spot. And this one is lighting and slowly turning up, because this time, once this is fully discharged, this will now go back to the original state. So that is the operation of Monostable Multivibrator. And we have now this simplified block diagram, and I introduce this header. We have this output line at the center. This is a voltage supply. We have two voltage supply header here, connection for future use. That is the header, this side one, and at the center I connect it to the output. We can use the additional line here for the future output. See that, connected to the header. And this one is the PCB layout. As you have seen here, I use a lot of resistor because that is the exact value according to my calculation. I'm using the exact value, that's why there's a lot of resistor. Also parts here, the transistor, resistors, the capacitor I use 10 microfarad for debounce, 100 microfarad for the discharge for the coupling capacitor, and also perf board, LED green, header, jump wires, perf board. So we have now these new features, LED power on and a header. That's the new feature. And we have now this circuit. Same as this circuit. The only difference is it has no LED power on indicator. That is the operation of Monostable Multivibrator collector coupled transistor. And this is the stable state, the current lows. And this one is the quasi stable state. Transistor here is off. It means whatever the appears to be the voltage output here is the voltage supply. But here the voltage output is 0. Here 0 or logic 0. But here the voltage output appears to be the voltage supply. And this is in logic 1. From 0 to logic 1. That is the computation. We have now this circuit diagram, PCB layout, parts here, PCB layout, transistor, and some probable calculation. And thank you. Bye bye.